Hello everyone, my name is Kamirul and I am presenting our recent work titled Sparse RCNN OBB Ship Target Detection in SAR Images based on Oriented Sparse Learnable Proposals. This work is a collaboration with Odysseus Papas and Professor Alina Kim. We are part of the Visual Information Laboratory at University of Bristol, UK. We are honored to present this research here at the IEEE International Conference on Image Processing ICIP 2025.
Before we dive into the details, let me walk you through the outline of today's presentation. I will start by introducing the problem and the motivation behind our work. Next, I will briefly discuss some existing approaches and how our work relates to them. Then I will explain the structure of our proposed model and key design choices. After that, I will share the experimental results and performance analysis. Finally, there will be a conclusion at the end of the slides. Ship orientation in SAR image is very important for tasks like route prediction and collision avoidance. Traditional detectors use horizontal bounding boxes, which is shown on the left, which don't align well with the shape of the ships. This leads to inaccurate detection. In contrast, oriented bounding boxes, shown on the right, align with the ship's actual direction and dimension, which gives a better accuracy. Since the SAR images are noisy and complex, our focus is on developing deep learning methods for oriented ship detection that work well in this challenging situation. Traditionally, detectors like Sparse RCNN use dense anchors, which means that thousands of predefined boxes are placed over the image, many of which are redundant or irrelevant. This is shown on the top diagram. Sparse RCNN replaces these dense anchors with a small set of learnable proposals, as illustrated in the lower diagram. These proposals not only carry box coordinates but also learnable box features, which are refined through the interaction with the image features. This approach eliminates the need for region proposal networks and non-maximum suppression or NMS post-processing, making the pipeline simpler and more efficient. Now, what makes this especially relevant to our study is that SAR ship detection fits naturally into the sparse proposal framework. These ships in SAR image tend to be sparsely distributed, so using sparse proposal, which focus only on a few meaningful locations, align perfectly with this property. To the best of our knowledge, the use of sparse proposal for detecting oriented objects in SAR image, especially for ships, has not yet been explored until now. In this study, we introduced Sparse RCNN OBB, which extends the Sparse RCNN to oriented bounding boxes and adapts it to specifically for ship detection in SAR images. This slide shows the full architecture of our proposed model. We begin with a standard backbone and feature pyramid network, or FPN, for extracting the features. The core change lies in the proposal generator and detection head. In traditional sparse RCNN, proposals are four-dimensional, encoding the box center, width, and height. But for oriented bounding box, we extend this to 5 dimensions by including the rotation angle. This brings us to the two key modifications in our architecture. First, the proposal boxes are now 5D to represent the rotation, and the second is that the regression branches is adapted to predict these 5 parameters instead of the usual 4. In the equation 1, we show the mathematical formulation used during the regression. Given the initial proposal parameters and the predicted deltas, we compute the final bounding box coordinates by using this equation. Finally, as the heart of the interaction, there is a dynamic head which interacts the objects and ROI features and feeds them to the classification and regression branches for the final detection output. We will discuss this dynamic head in the next slide. Instead of using fixed detection head, our model uses a learnable dynamic head that adapts to each proposal instance. This module is very crucial because it allows the model to learn rich interaction between the proposal features and the corresponding ROI features. Zooming into the bottom part of this slide, the dynamic hedge consists of two key components. First, self-attention module on the proposal features, which allow the proposal to exchange the contextual information. And the second is the dynamic instant interaction, where a unique set of parameters is generated for each proposal to modulate the ROI features. Basically, dynamic interaction is a weighting mechanism for modulating the ROI features based on proposal-specific parameters. In this process, each proposal generates dynamic parameters through a linear layer. These parameters are then split and used to transform the ROI features in two sequential steps using batch matrix multiplication, normalization, and ReLU activation. And these mechanisms enable each proposal to interact with its corresponding ROI features in a unique way, which is to learn what to emphasize and or to suppress based on the proposal contents. Our model was trained on public RSDD SAR datasets, which provide annotated SAR image of ships in both inshore and offshore environments. The detail of this dataset is given in the right table. We trained for 150 epoch using ADAM-W optimizer. Finally, we use average precision or AP as the evaluation matrix. AP is defined as the area under precision recall curve, which is formulated in equation 2. Specifically, we use also AP50, which requires a minimum intersection over union or IOU score of 0.5 between the predicted and ground truth. Additionally, we employ also AP50 inshore and AP50 offshore to evaluate our model in various environment. Here are some qualitative results comparing our model's prediction with ground truth annotation. The green boxes represent the ground truths and the magenta boxes are the model's predictions. We show examples from two types of environment, which is inshore and offshore. In both cases, the model performs well. However, the inshore scene is particularly challenging due to the clutter and interference from nearby objects such as docks, land structures, and other man-made objects. Despite this, our model is able to accurately distinguish ships from surrounding noises, even when the background features are visually similar. This highlights the robustness of our approach in complex and noisy SAR environments. These tables summarize the performance of our model compared to several state-of-the-art detectors. As you can see that our model achieved the highest overall AP50 of 95.88, and it also ranks first in the inshore detection with 91.44%, outperforming all the other methods in this challenging environment. And it holds up well offshore too, with a second best score of 66.25%, just slightly behind the CFA. This result demonstrates that our model delivers balanced and robust performance across both clutter inshore and open offshore scenes. To wrap up, we present Sparse RCNN OBB, our method for oriented starship detection in SAR images. Through 5D sparse proposals and dynamic instant interaction, the model achieves state-of-the-art results, excelling in both inshore and offshore regions. For the future works, while this model is already competitive and dominates the performance on most fronts, especially in offshore, we recognize that inshore detection remains more challenging due to dense background and clutter. To address this, we have taken the next step by developing a new model called Sparse RCNN, which is specifically designed to further improve detection in the complex inshore scene, to be precise. If you are interested in these details of work, you can visit the paper on IEEE Explore. This is the end part of my presentation. I'm happy to take any question you may have. Thank you.